Today's lecture is our Introduction to Equilibrium. Up until now, chemical reactions that we have observed have all been a reaction or a set of reactions that go to completion. For example, let's say we had a silver nitrate that was going to react with sodium chloride, and we were going to produce silver chloride as a solid for our precipitation reaction, and then we'd have sodium nitrate. We've drawn one directional arrows right here because these reactions go to completion. There is a subset of reactions that are defined as equilibrium reactions. Equilibrium reactions do not go to completion, and instead they establish a certain ratio of products to reactants in your closed container. An example of an equilibrium reaction would be when you react nitrogen gas with hydrogen gas at a particular temperature and pressure. You can get that to form ammonia in the gas form. Let's balance that. We need a 3 there. So we use a two-directional arrow to show that we've established an equilibrium in our container. When you establish an equilibrium in your container, what you are saying is that the rate of the forward reaction equals the rate of the reverse reaction, whatever that rate value is. For our purposes in class, we're just going to call it simply X, moles per second. Whatever X is, that rate at which the nitrogen and the hydrogen are combining together to form the ammonia, you establish an equilibrium in your container when the reverse rate, when the ammonia is breaking down to form hydrogen and nitrogen gas at the exact same rate. If the rates of the forward reaction and the rates of the reverse reaction are the same, therefore the net percentage of material on the left side and the right side of the equilibrium will not change. Once those rates have been established, they are the same. The analogy that we use, one of several analogies that we use to describe equilibrium, would be a parking lot in a downtown on a busy evening. You're at a parking lot right at the time of the busy evening, where you've got lots of people going out to dinner and theater shows, et cetera, et cetera, et cetera. Eventually that parking lot's going to fill up. Once that parking lot is full, a line starts to form outside the parking lot. At that point, the parking lot attendant is only going to let in at the same number of cars that leave at one particular time. So let's say just one car leaves at a particular time. Well, then that parking lot attendant is going to allow one car to go into the parking lot. So at that point, you've established an equilibrium of the cars leaving the parking lot and the cars entering the parking lot. And those rates at which the cars, once the parking lot is full, those rates are the same. And that's the point at which you've established an equilibrium between the parking garage and the rest of the surrounding city from the parking garage. All right, if we go back to our slide here, most reactions are reversible under certain conditions, a closed system. And you have two types of equilibrium systems. You have physical equilibriums and chemical equilibriums. We are going to focus mostly in our class on the chemical equilibriums. As I showed you on the previous slide, we use reversible arrows to show that equilibrium. So your second example of an equilibrium, the iron ion combined together with a thiocyanate ion will form an equilibrium with the iron 3 thiocyanato iron, the thiocyanato iron 3 ion, complex ion that's shown on the right-hand side of that equilibrium equation. Now, we can collect concentrations at equilibrium and experimentally determine something that is called the law of mass action. The law of mass action tells us about the value that we get from the law of mass action tells us where we can find our most of our material in our closed system, whether the majority of the material is on the reactant side or on the product side. The formal definition of the law of mass action shown here is the fraction formed from the concentration of the products divided by the reactants raised to their coefficient from the balanced chemical equation. Now, I can't emphasize the next line on the screen enough. You use only aqueous solutions and gases in equilibriums. you have no solids or liquids in your equilibrium system. Now let's talk for a moment why this is the case. If I have a beaker and it contains potassium chloride in the solid form, that potassium chloride has a certain number of moles associated with that per volume. So you've got moles per liter in your container of the potassium chloride. If we were then to go ahead and put more potassium chloride in the solid form on top of that, we have increased the number of moles, but have also increased the volume in the same proportion. So ultimately, the concentration of the KCl does not change by adding more or removing some. Same with the liquids. Therefore, we do not include solid and liquid concentrations into the law of mass action, only your aqueous solutions and gases. Just below there, you have the generic formula. The lowercase letters, A, B, C, and D, are your coefficients. Notice that when you go from the equilibrium equation to the equilibrium expression, the lowercase letters become your exponents. So the lowercase a becomes the exponent for the concentration of A. The brackets that are shown in both of these represent your concentration. And we typically measure concentrations in our class in moles per liter from the previous lecture. Now, when we take the concentration of the products raised to their coefficient, in the generic example C and D, divided by the concentration of the reactants raised to their coefficients, we get a value. That value is called KEQ. We can determine where material is within our equilibrium by examining what that KEQ value is. More generally speaking, KEQ is the concentration of the products over the concentration of the reactants. For an equilibrium system, this fraction will be a constant value, and we call that constant value KEQ. KEQ is defined as the mass action expression. Now, the second part of this statement is really important. It has to be at a constant temperature. If you change the temperature, you are going to cause a stress on your equilibrium that is going to cause a shift in material to move from one side of the reaction to another, and therefore reestablish a new KEQ value. When the KEQ value is large, then the reaction favors the products. When the KEQ value is small, then the reaction favors the reactants. So by having these concentrations at equilibrium, plugging them into the law of mass action and solving for KEQ, we can determine, do we have most of our material still on the reactant side and produce very little products, or vice versa. So let's practice a couple of things. First thing I'd like to do is practice writing an equilibrium expression for the following reaction. So we're going to have KEQ, and that's going to equal the concentration of CO2, which is going to be raised to its coefficient, 8, then the concentration of H2O raised to its coefficient, 10. Then we're going to divide that by concentration of the butane times its coefficient raised to its coefficient times the oxygen concentration raised to its coefficient. And that would be an example of writing a KEQ expression. Let's go ahead and practice writing another one. Let's write the KEQ expression for this example shown right here. This one would be KEQ equals the concentration of FeSCN2 positive divided by the concentration of Fe3 positive times the concentration of SCN negative. One more practice problem. Let's go ahead and use this equation written on the board here, and we'll actually plug some values in and talk about what a KEQ value would be here. So if I were to write the KEQ expression for this second reaction listed on the board here, we'd have the concentration of NH3, which is squared, divided by the concentration of N2 times the concentration of H2, which is going to be cubed. Now let's say we had a couple of values here. Let's say the NH3 concentration at equilibrium is 2.3 molar. the N2 concentration at equilibrium is 0.010 molar, and the H2 concentration at equilibrium is 0.022 molar. We can take those three values and plug them into our KEQ expression that we wrote up above. So we'd have 2.3 squared divided by the 0.010 times the 0.022, and that needs to be cubed. I go ahead and solve for KEQ, and I get an answer of 4.9. Actually, with just two sig figs, we get 5.0 times 10 to the 7th. So we went ahead, did this calculation for just a moment to then briefly talk about the implications of this value we just calculated. If we go back to the previous slide here, we have the statements right here. If KEQ is large, it favors the products. If KEQ is small, then the reaction favors the reactants. So we have a KEQ value of 5.0 times 10 to the 7th. That tells us that we favor our products in this chemical equilibrium. Another way of saying that is that in this equilibrium, the majority of the material is going to be found on this side of the equation. You're going to, once it establishes equilibrium in your closed container, you're going to have very little nitrogen gas and hydrogen gas left in that container.